In this video, we're going to look at the final part of logarithms and exponentials we need to look at. Now, we've covered graph transformations previously when we looked at polynomials and how they transform, how they change, and how we work them. What we're going to look at in this video is how we do transformations on the graphs of logarithmic and exponential functions. So what we're going to do is we're going to refresh our memory of what those graphs look like in the basic sense. We're going to refresh our memory of the way that we could transform graphs, and then we're going to look at a few examples of how we would do that for these types of functions. Now think back to when we did graphs of logarithms and exponentials. This is what the two of them look like. So on the left, the basic graph of the exponentials without any form of modification of f of x equals a to the power of x looks something like this. It's always a curve that goes up this way. It always cuts through 1. So it always cuts f of x equals 1 or y equals 1 when x is equal to 0 on the y-axis. And it always passes through this point here, 1, a. So whenever x is 1, f of x will always equal a to the power of 1, so a. So it always cuts through at this point. And in terms of where it goes, as you head off in x, it heads up in y towards infinity, and as you go down in x, in terms of the x direction, the y gets closer and closer to the x-axis, but will never ever touch it. Alright, it will always remain above this axis at any point. We can then look at the inverse one, so log to the base a of x, and that's given by this curve here. So it's a curve that comes up and around this way. Now remember that it's the inverse of the a to the x. So you could imagine if we took the a to the x and we plotted the line y equals x on it to draw the inverse of it, so in this case the log to the base a of x, you would just reflect in that. And if I reflect it in that line, this is how the graph should look. So the point on the y-axis where it cuts, which cuts at 1, goes to 1 on the x-axis, and the point at 1, a reflects in the line and goes to the coordinate of a, 1. So all the x and y values just swap. And this is what the generic curve for log to the base a of x looks like. Always cuts at x equals 1 when f of x equals 0. It will never ever cross the f-axis when it's a standard curve. When it gets transformed, maybe, but the standard curve will never ever cross the f of x axis. And again, it heads off to infinity as x goes up to infinity as well. And y in either direction, it'll head off to infinity and negative infinity. That's what the basic graph looks like for both of those. And we need to know that before we transfer them at all. One thing we also need to remember is what each of the transformations mean when we covered them back in the first unit. And these were the main 6 transformations. So we either had a times f of x, f of bracket a times x, f of x plus a, f of x then plus a, negative f of x, or f of negative x. And each of these did a slightly different thing to the curve. So af of x would stretch or squash the curve in the y direction, i.e. it would take its maximum and minimum points and stretch them up and down in y. If a was bigger than 1, it would stretch it, so it would grab it and it would move the points higher and lower and just stretch it out. And if a was between 0 and 1, we don't worry about the negatives just yet, that would squash it. So it would squash it in the y direction. For f of xa, sorry, if our f of ax here, where the a was acting on the x, this would have an effect in the x direction. It would stretch it or squash it in the x direction. The only difference being is that the bigger numbers would actually squash it. Think back to when we did the trig curves. If we had sine of 2x, that told us that the curve repeated twice within 360 degrees. Same idea here. So if a is bigger than 1, it actually squashes it in the x direction. And if a was between 1 and 0, it stretches it. So it's kind of the opposite of what you'd expect. F of x plus a, it would move up or down by a. So it would take the entire curve and shift it up by down. Or up or down by a. If a was positive, it would shift it up, and if a were negative, it would shift it down. So every single point would shift up or down. And the easy way to think about this is your x point would stay the same, the y coordinate would add the a on, or the x would stay the same and the y coordinate would subtract the a, depending on whether we added or subtracted. F of x plus a, it moves left or right by a. But here's the big difference. Again, if a is positive and we add on, it actually moves in the negative direction. And if a was negative, it actually moves in the positive direction. Again, it's counterintuitive. It does the opposite to what you would expect. So in this case, if we added a on, this first one here, we would subtract it from the x part of the coordinate. And if we subtracted a like we did in the second one, we would add it onto the x. So it shifts it the opposite way to what your intuition would think. Negative f of x we reflect in the x-axis. So we take the curve and we literally just flip it about the x-axis. So every single one of the coordinates that we would know, the y part of it would flip. So we'd end up going from xy to x comma negative y. And f of negative x reflects in the y-axis. In this case it's the x part of the coordinates that gets affected, and it goes to negative x comma y. That's what happens when we do that. So they are the 6 different types of transformation that we know how to do with curves. And this here is kind of the generic overall way that we can represent and write a curve to look at all the transformations. Now, when we covered this, there were a certain way that we covered it in a certain order we looked at them in. We always focused on the bracket part first, and our first one would actually be the bx. Our second transformation we would look at would be the c. Our third transformation we would worry about would be the a, and our fourth and final one would be the d, and that's going to hold out the same for looking at logs and exponentials. Right, let's have a look at a couple of examples of this and see exactly what I'm talking about. Imagine I've got the curve y equals log to the base 10 of x plus 1 take away 1, and I want to sketch it. Well, that is taking y equals log to the base 10 of x and doing these 2 transformations to it. So the first thing we should really do is figure out the order we do it in and then do them one at a time. Now, there's nothing in front of the x, so we don't need to worry about that. Our first transformation, though, is this plus 1 in the bracket here. We then look in front of the log to the base 10. Nothing there, so we don't worry about that. And then our second transformation is going to be the take away 1. So that's the first set of transformations we do to do the curve. So the x plus 1 here, think back to what it did. Anything affecting here, change the x direction. We've added 1, so again we go against our instincts. We don't go up by 1. All the points shift down by 1. So the one that would normally be at 1 here goes to 0, so it's going to cut through the origin. And our point that would be at a comma 1, well, remember a is 10, so it would be at 10 comma 1, moves down 1, so that then shifts to there, and it would be at 9 comma 1. So the curve would look something like that. Now remember, it's a sketch, so it doesn't have to be beautiful. Remember, the original curve doesn't cut the y-axis, however we've shifted it, so now it can. It can shift it then. So that would be y equals log to the base 10 of x plus 1. But we've got one more transformation to do. We've got this bit here, minus 1. So what that's going to do is take this whole curve and shift it down by 1. So if we were to then redraw that set of axes and draw in our final part of our transformation, this would shift down to here, so it would cut here at 9. This point here would be still on the y-axis, but it would be down at negative 1. And then the curve would just join up between the two of them like that. Correct shape done. There would be our 9 there. And we know that y equals log to the base 10 of x plus 1 minus 1. And remember to label your axes and all your curve. Remember as well, it's just a sketch. We have to get it looking roughly neat. It's not the most beautiful thing in the world. Now, sometimes breaking it down and doing them one at a time is fine. If we could break that down and do them both in one go, great. Don't put yourself under that pressure though. Make sure you can do the transformations before you try and jump ahead of yourself. Let's have a look at another one then. So imagine I've got the curve y equals 2 minus log to the base 8 of 2x, and I want to sketch that one right now. Well, again, I want to worry about the transformations. Do yourself a favour. If you've got a minus part here, switch them round and write negative log to the base a of 2x plus 2. It'll just make it slightly easier. Now for this one, we start by looking in here. 2x, so there's my first transformation there. Nothing else there. My second is going to be the negative part, and then my third is going to be the plus 2. So that's 3 different transformations that I've got to do for it. Now, log to the base a of 2x, that's the first one. What that does is that squashes the entire curve in the x direction. So it halves all of the different points in the x direction. So all the x values get halved. So it cut at 1. That now shifts in the way and goes to a half. The point that we had at a comma 1 So if we were to continue the curve up and out like that, the point that we had at a comma 1 goes to a half a comma 1. And that there is the first part of the curve, y equals log to the base a of 2x. Second transformation is the negative. Well, that's y equals negative log of this, so the whole of that curve then flips in the x-axis. All the values then flip. So what that does is instead of starting at the bottom and going up, it starts up at the top and comes down and around like that. None of these points change it in the terms of the x, so that's still at a half. The x of this still stays the same. The only difference is instead of 1, it goes to negative 1. And it goes to there. So that there then is y equals negative log to the base a of 2x. Our last transformation is then the plus 2, so everything shifts up 2. So this point here at a half comma 0 goes up to a half comma 2. This one here at a half a comma negative 1 goes up to a half a comma 1. So the final graph looks like that. It's still going to cut the x-axis. The only difference being is this point here, a half comma 0, goes up to a half comma 2. And the point that's there would be a half a comma 1. That there's my final curve. Y equals negative log to the base a of 2x plus 2. That's the original curve that we had. That's our final version of the transformation. Again, sketch doesn't have to be beautiful. Correct general shape, correct characteristics, correct points marked on. That's to the logarithms. The transformations stay the same sort of way for the exponential. You just have to remember the curve and how it looks. So let's do one example of those. So imagine I've got y equals 4 times 2 to the power of 2x, and I want to sketch that kind of curve there. Well, that's taking the curve y equals 2 to the x and then transforming it. So it's 4 times 2 to the 2x. The first thing that happens is this is affected. So it's happening to the x first. So there's your first transformation. Your second transformation is then this bad boy right here. So our first curve that we're going to sketch is 2 to the power of 2x. Now 2 to the power of x, what that does is it cuts at 1 and all the points get stretched there. Well, 2 to the x stretches it in the x direction. So in terms of the curve, cutting at the y-axis, that's still going to stay the same. That's still going to be at 1, but the point that was along at 1 and up to a, that gets squashed in, and it's now at a half comma a. So that's what the curve looks like. That's y equals 2 to the power of 2x. It looks roughly like this. The next transformation is you then got to do 4 times it, so we multiply everything by 4. So we stretch the curve in the y direction by 4. Now, one thing to note, there's no negative values still in the y direction, so this is still not going to cross the x-axis. It's still going to remain positive. It's just going to get closer and closer and closer. So it's still going to have the same general shape. It's still going to look like that. This is going to get multiplied by 4, so instead of 1, it's going to cut at 4. And this is going to get multiplied as well. So that's going to go to a half comma, well, a would be 2 in this case, so it's going to cut at a half comma 8. That's where the point would cut in there. And that is y equals 4 times 2 to the power of 2x. That there's my graph with all the transformations done to it. Doing these transformations, regardless of whether it's a logarithm or an exponential function, is the same set of steps. We approach it in the same order. We look at what happens to the x first, then anything that gets added to that, then the numbers that multiply the f of x, and then adding or subtracting. It's the same set of steps as it would be for just a normal, ordinary polynomial type function. Right, your turn to have a shot at a couple. Here's 2 for you to do. Y equals log to the base 2 of the square root of x plus 1, and y equals 3 to the power of x, take away 2. Have a go at both of those. That's what we're going to start lesson with. See how you get on with it, and then you can get cracking with some work. Good luck.